Hello, everybody. Happy Monday. Today I'm back working on my drakon renderer engine again. What I want to show you today is something that is making me pretty excited. So during the last session and during the last some previous sessions, a number of previous sessions, you remember I considered a new way of laying out those icons on the display. I read some materials about drakon. I read the drakon white paper, and I started scratching my head pretty aggressively about what to do with connections like this. So according to my algorithms, connections like this are correct. The dependents are on the same level. But according to drakon, unfortunately, this is not considered correct. Now, I run some experiments, and maybe you remember our valent points. And those are specific points that may or may not host icons in the rendered version of the diagram. So with artificially inserted valent points, and maybe we will find an example, the diagram starts looking significantly more correct. I wouldn't call it perfect, but significantly more correct. Let's open it, maybe I can find it. But unfortunately, it also exposes a number of problems. Namely, maybe we can show it here. SVG, would that be good? No, I think it's vanished now. Maybe I'll just quickly check the issue. No, it doesn't. But you can probably revisit one of my previous videos to see that if you inject a valent point here, it straightens out this connection, making it look like a canonical drakon connection. Now, I've thought long and hard about how we could implement those valent points to aid in this problem of connections being drawn in an unusual way, let's call it. And I think I have some ideas. And not to spoil the surprise, and also not to jinx it, because if it doesn't work, I'll be very disappointed. I'll just tell you this. What I want to do is come up with a way that repositions or rebalances inputs like this. If you get an input, an icon in the input that has two dependents, out of which one dependent depends on the other one, generating this strange loop, you really need to rebalance the tree, right? This dependent as a dependent of this, and this cannot really be on the same position. It needs to be a little bit lower. So I'm thinking to rebalance the diagram that we generate by taking loops or cycles like that. Well, not really cycles. They're not cycles, or they're not really loops, but they are sections, let's call them generically. If you have a section of the graph that contains diverging branches that converge later on, like here, you need to really rebalance it. That's what I'm thinking and hoping to do. Namely, all branches need to be of the same length. Namely, all branches need to contain the same number of valent points that may or may not in the future host inside of them icons. That requires a number of changes, right? So I've added those valent points to the graphs as a sort of as a gimmick. Maybe you remember during one of my previous sessions, those valence points were treated as just regular icons. But I think we'll have to change the approach slightly and have the valence points be the primary citizen of drakon graphs, and they may or may not host quote unquote actual icons, whether actions or questions or whatever it is, so that every step of the diagram that can be occupied is occupied first by a valence point, and later on inside that valence point or on top of that valence point we may have actual icons like this headline or like this question. Now, I think approaching diagrams like that, meaning every step needs to be occupied by valence point, will simplify our layout algorithm and the connection algorithm by a large margin. But in order for us to achieve that goal of every step being populated with valence point, we need to think of a way of rebalancing these sections of branches that are diverging first and then converging, making them of equal length. And well, I probably should stop using the term equal length. I should start using terms like we should make sure that each branch in this section that is diverging and then converging contain equal number of valence points, right? In this case, the valence points that we would identify is the starting one and the end one, and this branch only has two. And if you follow this branch, we have one valence point that hosts the question, one valence point that hosts another question, and one valence point that hosts the action. So that's three. So we see immediately that there's an imbalance. We have two branches diverging here. This of count three, where we have three valence points. This branch has two valence points. So what I was thinking, or what I've been thinking about for the last days, is a pretty easy to maintain and grasp algorithm of injecting programmatically valence points into user-provided input, so that the user is not really exposed to this ethos of designing in drakon, but yet you render in correct drakon and the diagrams are really following drakon procedures. So I think I have an idea how to programmatically inject valence points, but I don't want to give it away just yet, just in case it doesn't work. I want to have some fun with the code to begin with. So what I'm thinking to do in the first, as the first step, is to identify those sections where branches diverge and then converge. And the method I have for that is pretty straightforward, I would like to think. So branches converge where one dependent is a dependent of many different icons, right? And here is a function that I prepared off camera that shows a dependent name, like for example, dependent 6. I think this is dependent 6. Dependent 6 has two parents, or two icons have icon 6 as their dependent, icon 3 and 4. This is icon 3, this is icon 4. So if you comb the icons with this initial algorithm finding convergence points, you will immediately find those convergence points. And in this algorithm, in this diagram, we only have three. Convergence point end, which is a meeting point of three different connections. 1, 2, 3. But we're going to ignore it for now because I don't want to mess with the silhouette diagrams just yet. And here you have convergence point 6, which is here, and also convergence point 8, which is here. which is a meeting point for icon 6. Yes, and also icon 7. So now, the function that I wrote, I think, if I remember correctly, is here in the main module. It's called map of parents. So you have here a dependent, and it's the list of its parents. So out of this list, we would only be interested in this and this. And I also conversely need to come up with a function that maps dependence in order to find divergence points, where the branches start coincidentally branching out. So we can capture these points as a result of my off-camera experiments. Now, today, we're going to try and implement a similar function which will detect the divergence points, where the branches start branching out. So, given this lengthy introduction, I hope you're not bored to tears. I'm having lots of fun with this rendering engine. I hope you stick around. Now, let's try to write this function. And so the function we'll need is this is going to serve as a map of dependence. The description is pretty vague, but we're going to use it to map the divergence points. And maybe you know what? Before we do that, let's modify this function to not return everything, but instead to only return dependents which have more than one parent. How do we do this? Well, first of all, when where we have this function data map insert with, let's modify it so we only insert if the icon kind is not end. Because if we have end, we'll introduce a number of problems, meaning if you follow the algorithm I want to propose, and if your convergence point is the end, well, ultimately all of your icons will start diverging from somewhere here. So you'll be rebalancing the whole thing. And the question is, do we want that? Or do we want to rather focus on subsections of the tree, or the diagram? So just for the sake of simplicity, I'm just going to focus on icons that are not end. So here, case. Let's revisit the data types. If this is an end, we just want to return the accumulator. We don't care, but if it's anything else, we want to add to the accumulator. Let's see if this builds. I hope everybody had a great weekend, by the way. I got so excited trying to explain this that I forgot to make sure. I did. Let's see what we get. I see we still get 100, which is the last one, which is not exactly what I needed. Oh, I think I'm checking the wrong kind. Obviously, if you're a parent, you cannot have dependents. Sorry, if you're a parent, sorry, if you're an end, you cannot be a parent. You cannot have dependents. So let's do this. Oh, that could be a little bit harder than I thought. Let's approach it a bit differently. It's not the part that we should be checking, it's the dependent. So I think a final sweep is in order here before we return parents. That goes something like this. Filter. And let's check the data map. Query. So we need to look up Let's see if this works even. Um, will this work? Oh, I'm not sure if it worked like that because let's not forget this is not just an ordinary list that we're returning from this fold. It's a map. Therefore, it can't be just that easily filtered. But you know what? For now, maybe I'm getting ahead of myself. I'm sure we can get to this state where we only return non-end um, elements of the map where we have multiple parents. But for now, for today, I only want to focus on finding the divergence points. So we'll have something very similar to this, where we go through icons and let's implement the first fold for now. Where we start with an empty map. For now, let's call it just accumulator. Maybe we can get away with just one. I think we should be able to get away with just one. Yes, of course, because every entry here, and this is all icons, all these need to be unique. Oh, but these also need to be unique. We'll get there. For now, let's worry about just one fold. So for every icon, where's the insert with? Let's not forget this is not correct. So we can remove it. For every icon, we insert it is worryingly similar in code. And again, what we're trying to do is to capture a list where the key is the parent name, not a dependent name, and the values are dependent names. And it is going to be very similar. Dependence like that. In. At this time, the situation is going to be inversed. Parent name, dependent name. So, names. And ACC is like this. Let's try to build it. Oh, sorry, dependent names is already a list, so we don't have to surround it with square brackets. Oh yeah, but now it will suggest a reduction. Like this. Okay, let's run it. Oh, before I run it, let's actually execute this. So here we have the map of parents. AKA potential convergence points. And map of dependence as a potential list of divergence points. Okay, so what do we have here? So let's call this I'm sure it's easy to read when you're watching it, but to me, these fonts seem enormous. Okay, so 2 is a dependent of 1, that's correct. This I don't remember. 100 does not have any dependence, that's what we remember. Icon 3 has 2 dependence, 4 has 6, 4 has 1 dependence, 4 is 6, that's correct. So here, I think this is fine. And this is good. So what we are interested in is, in the next step, we want to isolate sublists. Sublist number 1 is going to be all the points where branches of or paths of the graph start diverging. So it will be this. Let's call it potential divergence points. Or no, this is dense. And here, because these are not necessarily divergence points or convergence points yet, these are potential. And this is dependent parents. And here, as you've noticed, we don't have the title icon. So we're expecting to see something like this. I'm going to copy this whole list. So nothing is diverging here or here. We have branches diverging in 3 places actually. That's a lot. Okay, and we have convergence, potential convergence points here. So these are not potential anymore. These are for sure convergence and divergence points. Oh, sorry, it's reversed. This is where branches start diverting or diverging, sorry, and this is when they do converge. And what is interesting is that we have 3 convergence points, including the end, which we want to exclude. What is this, JSON? And we have many divergence points. So this is something that I already see as valuable. I'm not sure why I thought that we would have the number of convergence points equal to the number of divergence points, but I don't think that's going to be necessarily the case. Can we see an example of this? Well, here, if we had 1, 2, no. Let's see a real life diagram. Oh, here. We have 1, 2. Yeah, we have 2 divergence points, but only 1 convergence points. Convergence point. Is that a good example? Let's see. Let's see the latest version of my diagram again. This is not it. This is not it. Oh, goodness, sorry. Real life. Okay, so we have 1, 2, 3 divergence points. Why do we have 4 here? Oh, sorry, this guy. 1, 2, 3, 4. Yeah, add convergence points. We have 6. That's 1, 2, and 3. Oh, so this is a good example. We have the ratio of 2 divergence points to 1 convergence points. So the numbers might not add up. But either way, I don't think it makes sense to scan the whole tree to balance it. Also, it would be very difficult. I think focusing on the sorry, when I say tree, it's not really a tree, is it? It's a graph, a directed graph. Focusing only on subsections of this graph makes much more sense to me when it comes to balancing. So, okay, so this is the homework for another session. We're excluding this because this is end. And in the session following, me being able to figure this out, we'll have to find ways to identify paths that lead from a divergence point to a convergence point. So something like, let's say we're dealing with the pair of this 3 and 6. We would have to find paths starting in this convergence point and starting at this divergence points and finishing at a convergence point. So if we were to follow this parent and all its dependents, we would get 3 leads to 4, but also 3 that leads to 6. And then 4, we know that 4 leads to 6, and 6 is already at the end. So here is our first branch, which is here. So we would know that we need to insert a valent point here, valent point 1, so the path looks something like this. But that's in an upcoming, a future session. During the next session, I would like to be able to identify a narrowed down list of divergence points and convergence points. So having said that, I think we're going to wrap it up for today. Thanks very much for your patience, and I'll see you next time. Bye.